So tides are generated by two primary forces, both associated with orbiting bodies. In order to get anything dense enough to generate interesting gravitational fields in this lab room, we'd have to use some materials that are not commonly found on the surface of Earth or anywhere in the inner solar system. So what we're going to use instead to simulate the gravitational force that generates tides between the Earth and Moon is some magnets. What we're using instead of seawater here is a ferrofluid. So we're now going to watch what happens to the surface of the water as we move the magnet closer to it, to the bowl, simulating the gravitational pull of the Earth's moon. So this gravitational force, in this case we're using magnets to simulate gravitational force, but in the actual universe this would be gravitational force, starts to pull the fluid towards it, creating a tidal bulge towards the moon, represented by this magnet. I'm going to rotate our camera just a little slightly to better visualize the tidal bulge here. But this one will explain why, but in this universe, the moon would eventually crash on Earth and we'd not be happy. What we know instead happens is that, of course, the moon and the Earth orbit a common barycenter, a sort of center of gravity between the two masses. And so the Earth, we're going to now cause these two bodies to go in orbit because we're using a turntable. Watch what happens to the fluid as we start rotating. What you should be able to see now is a sizable bulge is now being directed outward, away from the moon, by the centripetal force in this system. We're going to dial it down just a little bit. It's going a little faster than we're comfortable with, but what you should see in here are two distinct tidal bulges toward the moon, simulated by the magnets, and opposite the moon. If we're lucky, we might even see the tidal bulges getting a little sort of area of low tide perpendicular to this axis. All right, we're going to stop it and we're going to stop it one more and start it one more time and see what happens to the tidal bulges. Stop it. So then if we stop the rotation, the tidal bulges have returned to their original position. Or we still have the lunar gravity tidal bulge, but we don't have the centripetal tidal bulge. Now turn it on again and watch how the tidal bulge evolves. Hmm. So we've now watched a tidal bulge form on both sides and disappear. We also remove the magnet from the system to return the system back to its original position once it stops rotating. As you might imagine, trying to detach a magnet from a rotating body is going to be a little sketchy, so here we are.